A very good day, everyone. So, imagine a busy water treatment plant or an HVAC system keeping skyscrapers cool. Behind the scenes, butterfly valves are quietly working to control fluid flow. So, I'm Diroshan Raj Analaki Ilongo, and today I'll be I'll walk you through my project, which is CFD analysis of flow rate influence on pressure drop and turbulence in a butterfly valve. This project was part of my MMK 36003 computer aided engineering 2 course at University Malaysia Perlis. We'll dive into how these valves perform under different conditions and how we can improve their efficiency. Let's get started. So, have you ever wondered how engineers balance efficiency and stability in fluid systems? That's where this project comes in. We had three main objectives, and the first one was analyze how varying flow rates influence pressure drop across a butterfly valve. And the second was to study turbulence intensity distributions downstream of the valve. And the third one was provide insights into optimizing valve operation under different flow conditions. These insights are crucial for saving energy and enhancing operational stability in industries. We used CFD or computational fluid dynamics to stimulate the internal dynamics of a butterfly valve. Using SimFlow software and the K epsilon turbulence model, we studied how different flow rates and valve opening angles impact pressure and velocity distribution. And what did we find? Higher flow rates and large valve openings caused significant pressure drops and turbulence. For example, when the valve was at 40 degrees opening and the flow speed reached 15 meter per second, we observed peak turbulence and pressure drop. This study provides a roadmap for optimizing valve operations to minimize energy losses. So, why butterfly valves? Well, they're everywhere, used in water systems, power plants, and even factories. Their compact design and efficiency make them a favorite for controlling fluid flow. But here's the catch. Their performance is sensitive to flow rate and valve angle. If not optimized, they can cause unnecessary energy losses and turbulence. Previous studies have used CFD to understand the valve behavior, but this project goes a step further for by stimulating multiple flow conditions and analyzing their impacts. So this is the flow chart of the simulation. So first, we start the simulation process. First of all, we will create or prepare the geometry in CATIA, and we will export the finished design to in STL file, and then import the STL file into SimFlow. And then the next step would be mesh generation, and then after mesh generation would be mesh quality check. So if the mesh quality checks is all fine without any errors, we can proceed to the next step, which is boundary condition setup. But if the mesh quality check shows an error, we should move a step backwards, which is to mesh generation, where we should do mesh generation again so that the mesh quality check will turn out without any errors. So after boundary condition setup, we will move to solver setup, and then we will run the simulation, and then later on we will do a post processing about the results. Now, let's look at how we carried out the study. We started by designing the valve geometry in CATIA software and created a structured tetrahedral mesh with around 192,000 cells. The mesh was fine-tuned to capture detailed flow behavior near the valve. In SimFlow, we applied the following simulation settings. For solver setup, we set the steady state with the simple algorithm, and for turbulence model, K epsilon was perfect for analyzing industrial fluid flows. And while for the test cases, inlet velocity is set to 5, and then later on to 10, and then to 15 meter per second. While for the valve opening angles were 20 degree, 30 degree, and 40 degree. And the boundary conditions: velocity inlets and pressure outlet with no slip walls. Now, here's where things get exciting. The results. Effect of valve angle. At a 20-degree opening, the maximum velocity reached is 69.2 meter per second. But as the valve opened wider to 40 degrees, the velocity dropped significantly to a 10.9 meter per second. Similarly, the pressure dropped from 4027 Pascal at 20 degree to just 73.5 Pascal at 40 degrees. This means narrower openings cause more turbulence and resistance, while wider openings allow smoother flow. And the next is the effect of inlet velocity. Higher inlet velocities directly increase both velocity and pressure. For instance, at 15 meter per second inlet velocity, the maximum pressure jumped to 15,327 Pascal, which is almost 800% higher than at 5 meter per second. These findings highlight the importance of considering flow rates during valve design. To make this more visual, I've included graphs and color-coded contour plots showing velocity and pressure distributions for each test case. We will look that in the next slide. So this is the graph that we have obtained. The graphs that I have obtained is maximum velocity versus angle of plate, and the maximum pressure versus the angle of plate, and maximum pressure versus inlet velocity, and also the maximum velocity versus inlet velocity. So this is the structure of the graph. So now let's move on to our color contour plots. And for case one, which is the valve opening of 20 degree, this is the color contour plots for maximum velocity and maximum pressure. And this is the for valve opening of 30 degrees, the color contour plot for maximum velocity and maximum pressure. And this is for the valve opening of 40 degrees. As you can see, there is a lot of difference in maximum velocity compared to the other two color contour plots. And this is and now the case 2, which is 5 meter per second of inlet velocity. As you can see, that is the maximum velocity and maximum pressure. And then for 10 meter per second and 15 meter per second. So now let us move on to discussion. So let's interpret these results. Narrower valve openings act like bottlenecks. They create higher turbulence, increased velocity, and large pressure drops. On the other hand, wider openings reduce resistance, allowing smoother and more efficient flow. What does this mean? In practical terms, we don't optimize valve settings. We risk wasting energy and creating unstable fluid systems by carefully choosing valve angles and flow rates. Industries can save energy and reduce wear and tear on their equipment, which is the last part is the conclusion. So, in conclusion, this project achieved its objective. We quantified how flow rates and valve angles impact pressure drop and velocity. The results showed that optimizing valve settings can minimize energy losses and improve system stability. While for future studies, we could explore transient flow simulations to understand time-dependent behaviors, the impact of material properties and surface roughness on valve performance, and ultimately these findings paved the way for more efficient and reliable industrial systems. So thank you very much for watching and hope you guys have a great day.